Hey folks, Todd Coburn here with your Aerospace Structures series. This video is going to continue our study in dynamics. We're going to be looking at kinematics of particles and are going to be focused on curvilinear motion. Stay tuned. Some examples of curvilinear motion we can see in the motion of an aircraft when it goes through a banking action. We can see that it describes how a bat moves through the air and even the trajectory of the ball. And it also describes how you will experience motion if you're going down a winding road. This word curvilinear, at its root, basically just means that we have motion where the path or the trajectory is non-straight. So any particle moving on a non-straight path can be described with curvilinear motion. Okay, so that's what we're going to be studying. We're going to be learning the different ways of evaluating that. We can use this graphic to describe our study. Now what we have here is we have an arbitrary frame of reference that we're going to identify with a coordinate system, and we're going to imagine yourself sitting at point O, and so we'll call that the origin. We've defined our coordinate system. We'll just make X to the right and Y up. You'll notice we're looking at a plane. All of our motion is in a plane. We could also extend this to three-dimensional motion, but right now to keep it simple, we'll focus on just planar motion. You can see we have some kind of particle which happens to be at point A at one point, and we can see it's on a path, a trajectory, and you can see that trajectory, shown by the orange arrow dash line, is non-straight, therefore it's represented with curvilinear motion. Now you can actually use the equations we're going to lay out here for either rectilinear straight line motion or curvilinear curved motion, but we're going to develop it generally so it applies to curvilinear motion. We can always use that for straight line as well, with a couple tweaks in places. So imagine we have this particle. We're looking at it from point O. Now we could talk about the position of this particle as just a set of coordinates, X, Y, Z. But it actually is useful and more general and easier to do more things if we define it as a vector. Its position as a vector from the reference frame, or the place where we're looking from, the observation point, which is in mathematical terms just our coordinate system. So instead of talking about the position at A with an XYZ, we will talk about the position at A as a vector from the origin. We're going to call that vector R. It's shown boldface, which is our way of showing that it's a vector. We can show vectors by making them boldface, by putting a line over them or an arrow over them. There are a lot of different ways to do that. We're going to use, at this point, that R. This little graphic is from Merriam and Crage's book, Dynamics. There are similar pictures in Beer and Johnson. You're going to see a lot of Merriam and Crage and a lot of Beer and Johnson figures here, because those are two great books, and if you need a good book to follow along, choose one of those is great. You won't go wrong. That'll give you a lot of more information beyond my lecture, and it also will give you example problems to review and also to practice on. So we have this particle at point A, and it's defined by its position vector R. That position vector R, although we're not specifying it only with its coordinates, we can use the coordinates X, Y, Z with the unit vector I, J, K. Now, since we're talking about planar motion, we can ignore the K and just talk about I and J, which means we can have the X position I, which shows the direction, Y plus Y position, J, which makes this a vector identifying the position of point A at some point in time from the origin. Now later along the trajectory, we see that the same particle is at point A prime. Okay, now going from A to A prime, since our vector, our point was initially at point A with this vector R defining where it is, we now can say, well, from A, it's going to change a new position vector, which we can call delta R, the change in R. The new position could be defined as R plus delta R, the initial vector to the position plus the secondary vector to the new position, and that is a single vector r plus delta r, as you see here. So we see the r vector, we see the delta r of how it changes from A to A prime, and then the kind of true position vector r plus delta r, which defines where that second point is relative to our origin or our reference point or our viewing point, okay? So going from A to A prime, we've got delta r. That's the change in position vector. And that also, we could say a lot of times we're using, now we're using r for this position vector. S is a lot of times used as position in dynamics, where we'll use S instead of saying X or Y. S is a generic term that we can use to talk about what the magnitude of that position is, okay? So we got the idea of a plane. Right now we're just focusing on planar motion, and the same stuff will apply in three-dimensional. We'll just have more terms. Curvilinear, which means you have motion that's not straight. We have R, which is our position vector, which is typically identified as an I, J, K kind of thing. We've got an X coordinate times I, Y coordinate times J, potentially a Z coordinate times K. Delta S is just the change in position. It's just the magnitude of it. We're going to use S as a scalar kind of value. And T is the time that's elapsed. Whenever we talk about position, we should also talk about time if we want to understand the kinematics of that motion, what change happened over what period of time. So we can actually define our velocity as the change in R, the position vector, over the change in time. Now this is the average value. Why is it the average? Well, we kind of probably imagine that this thing is moving at a constant velocity, which if it is, then this is also the instantaneous velocity. But we really don't know. If we take a picture, let's say, of the particle at point A, take another picture at point A prime, and we measure the time between them, all we know is that the change in position over that time is the velocity, or the average velocity between here and here. We don't know that it was constant. We don't know precisely what the value is. Why? Well, we could have been going very fast and been slowing down the whole time, have two different velocities. We could have been going very slow and been speeding up the whole time. We could have been going slow, sped up, and drop back down to a slower speed. Who knows? And so, by this delta R over delta T, that just tells us about the average behavior from the one point to the other. Got that idea? Okay. Next, we could talk about the speed. So this velocity vector, dr dt, since r is a vector, dr is a vector, that means we're getting a vector, that vector speed, vector velocity. We could also talk about the scalar magnitude of the velocity, which is just the change in the magnitude of the position, ds over dt, where ds is just a magnitude and with no position information. If you divide that by the time, that's going to give you the magnitude of the average velocity. Okay, pretty simple. Now, if we wanted to know what the instantaneous velocity is, what we would have to do is take that dr dt, and we would look at it as in the limit as the delta t gets smaller and smaller. As delta t gets smaller and smaller. So we know the average velocity going from here to here. As the delta t gets smaller, we've traveled less. And when that delta t is like near zero, we actually have the instantaneous speed, or an average that approximates the instantaneous speed. If that delta t was truly zero, but we weren't quite singular, we would know what the instantaneous speed is at that point. So that's typically how we do this. Of course, numerically, whenever we're dealing with this number, mostly we'll be sometimes in academia, we'll be playing with the continuous integral, but more commonly when you're doing this in industry, you're going to be using discrete numbers with a numerical kind of approach. So we're going to say, okay, at this delta t, we got this change in position, and therefore that's the effectively instantaneous velocity if that delta t is very small, and in fact, it's the average velocity over that, which can approximate the instantaneous velocity. You kind of got those ideas? Okay. So we can actually, one simplified, so dr dt in the limit as delta t gets small, we can just write it as dr dt, and a common shorthand for this is just r dot, which indicates that it's the derivative of that r with respect to t. So we're going to use that over dot to represent, whenever taking the derivative, or the rate of change with respect to time. Okay? All right. Our speed is just the magnitude of that. So if our position magnitude, or the change in position, is just called s, or ds, then we can define that magnitude of the change, which is the speed, as s dot. These are commonly used and are the same as the r dot, but r dot is a vector and s dot is just a scalar. Okay, this little graphic here shows the same thing out of Beer-Johnson. This is a Beer-Johnson picture here, or sketch here. Now you'll notice here we also, once again, are in planar motion. However, we're now showing the z-axis. So we can say, all right, this actually also applies to three-dimensional motion. In this particular case, it looks like all the points are at one z location, which makes it planar motion. But if any of them were out of plane, the same principles apply. We just need one more indice in our vector, the z-coordinate. Got that? So these are the building blocks of what we're going to be doing. A lot of what we're going to do is going to be the same as our first lecture on rectilinear motion, but we're going to be looking at slightly more general equations so that we can cover curvilinear motion. So if we look at this, now notice again, we have a reference point, that's the origin, where we are defining our coordinate system. We have the position point A, the particle A, or the particle at point A and at point A prime. Now, it's moving along the path and it has some velocity, otherwise it wouldn't be moving, right? If it's moving, we have delta r occurring over some time, and that means we have velocity. The instantaneous velocity at any point has to be tangent to this path. So we have the point, that particle at point A, we could draw a line or a vector tangent to the path in the direction of motion, and that tells us the instantaneous velocity at that point. Now, the acceleration, so the velocity is tangent, the acceleration not necessarily. If we take the velocity at point A and the velocity at point A prime, we're going to call that v prime, then the change going from the initial velocity to the next velocity is that delta v, right? So we've got an instantaneous velocity at point A drawn here. We've got an instantaneous velocity at point A prime. And in order to transfer the v of the first point, the velocity of the first point, to the velocity of the second point, we would have to have a vector added to v that gets us to the endpoint of v prime, which means we have that delta v, which with vector addition we see gives us v prime. So v plus delta v equals v prime. That gives us the new velocity. All right. Now the acceleration is going to be in that direction of change of velocity, because the change in velocity over time, remember, that's acceleration. So our acceleration is going to be in the same direction as that change in velocity vector. While our velocity the instantaneous velocity is always going to be tangent to the path at a particular point. So both velocities were tangent to the path at the points they were measured. But our acceleration is going to be the vector that matches the direction of delta v, and it's not going to be along the path typically, or perpendicular to the path typically, unless we have like a circle, and we'll talk about that later. So just some general curvilinear motion, that direction of the acceleration will often not be parallel to the path or perpendicular to the path. If we have a perfect circle, then it will be perpendicular. We'll be talking about that in a bit. Okay, so these are our basic ideas. We know that the velocity plus the change in velocity is the new velocity, v prime at a prime. We could define the acceleration as the change in velocity vector over the change in time vector. The velocity vector is a vector, and so is the change in velocity vector. And when we take the change in that with respect to the change in time, that gives us the average acceleration for the same reasons that gave us the average velocity on the last slide. The instantaneous acceleration is computed the same way. As we make delta t get smaller and smaller, we get something closer and closer to the instantaneous acceleration. which we can call dv dt or just v dot. V dot means we're taking the rate of change of the velocity with respect to time. A little graphic, those upper graphics are from Merriam and Crage's book. The lower graphic is from Beer-Johnson's book. It actually is planar motion because it looks like all this is in the same plane, but since we're showing the z, we could say this is three-dimensional motion. We just happen to be currently talking about the part that's confined to a plane. Okay, we said the acceleration in general is not tangent to the path and the velocity. So remember, the velocity is tangent to the path. The acceleration typically is not. The acceleration, we're going to find out later, will be perpendicular to the path for circular motion, but will tend to not be either parallel or perpendicular for non-circular motion. When we have curvilinear motion, it's defined in the same direction as this change in velocity vector, as you see from this graphic we talked about before. You got that so far? Okay. If you need to, you can rewind this video and rewatch this again. Rewind the video and watch it again. Or even better yet, take one of these books, Beer-Johnson's or Merriam Crage's, and read the corresponding sections of the book. You'll notice on my title slide, I tell you the corresponding sections where this is covered in Merriam Crage and Beer-Johnson, and also in Gray, Costanzo, and Pleshett or something. Yeah. Okay. So let's look at this even more generally here. We can see now where it's going to generally, so we learned a little bit about rectangular coordinates, polar coordinates, and spherical coordinates. Usually for most humans, and most of us are humans, we're going to find that the rectangular coordinate system is easier to work with in most cases. There are special cases where the polar and spherical coordinate systems will be better and will make our calculations easier. But in general, we're usually more comfortable dealing with a rectangular coordinate frame for any time that doesn't make the work harder. So that's what we're going to kind of focus on. So looking here again at three-dimensional motion, these pictures out of Beer-Johnson's book. We got a three-dimensional coordinate system with a coordinate system drawn, x, y, z. We're going to have a particle. Now we've got the particle P there at some point, x, y, z. So the position vector, r, is just the x times the I, right? That's your unit vector. I is your unit vector in the x direction. So the magnitude of the x from the origin times I gives us that value as a vector, the y times the j, and the z times the k. So xi plus yj plus zk is a vector, a three-dimensional vector that gives us the position. This vector could end up defining a straight line. It could end up defining a curved, a straight line in a plane, or a straight line in 3 space. Okay. So we can see this particle in 3 dimensions has some path. You can see with that dark line. We know that the velocity is going to be parallel to the path. We know that the acceleration is not going to typically be along the path. We'll learn about that by looking at the change in velocity. And we define that position vector r as the x position from the origin. So this is easier than it looks. If you take the particle and you measure what is the x coordinate in our coordinate system, multiply that by I, plus the y coordinate multiplied by j, plus the z coordinate multiplied by k, that xi plus yj plus zk is a vector r, which completely defines the position of the particle from the reference point at point O. Okay, so that's a vector. Our I, J, K's are vector. X, Y, Z's are just magnitudes, but altogether it defines the whole vector that defines where that point is. It's critical to understand this simple concept. Once we understand that, now we can evaluate the velocity and the acceleration with respect to change in times quite readily. Often we will take the equations and work with them as if we're working with scalars. And often we will take this vector and just differentiate it to get that velocity and acceleration. Both approaches can commonly be the best way. So the velocity is this derivative of this vector with respect to time. So it's just dx with respect to t, dy with respect to t, dz with respect to t, which we can call x dot, y dot, z dot. Remember, that's just another nomenclature for the derivative with respect to time, which we can just say is the magnitude of the velocity v in the x direction times I, plus the velocity, the scalar velocity magnitude in the y direction, plus the scalar velocity in the z direction. It seems like we're taking this apart and making it overly simple, but this enables us being able to define this vector any of these ways will give us a method of evaluating. Sometimes we use one little trick, and other times another little trick. Often we're going to be using trig for these pieces to come up with the component of the velocity in the x, y, or z direction. It keeps our analysis simple and familiar, keeps us with a three-dimensional vector kind of operation, and we can solve the mysteries of the universe with this. Much easier than it appears. Okay. Now the acceleration, remember the acceleration is just the derivative of the velocity. So we can take the velocity written as a position vector, the dx dt, just take the derivative again, which is now just the second derivative of that position vector with respect to time. While this looks ugly and a lot of engineering students are afraid of calculus, they start out being good at math, algebra, trig, and even calculus, and then usually calculus gets harder and harder until they start hating it and fearing it. Then they come into their engineering classes and they try to avoid it. But this can get ugly on us, but it can be quite simple using the easiest parts of calculus to solve these kinds of problems. So since we're taking the second derivative of this position vector with respect to time, that we can use a shortened notation. That's just the x dot, which is the derivative of x with respect to t. X double dot, the y double dot, the z double dot. So we just take the derivative again of our velocity vector. So we've got two ways we can do this. Did you catch that? We started with the position vector. The position vector is much easier to get than it appears. All you have to do is look on your page, sketch your problem, find out where that point is, come up with some coordinate system, x, y, z, and then define the position of the point by figuring out what is the x position, what is the y position, what is the z position. You multiply those components times the unit vector to find the vector as the xi plus yj plus zk. Then you take the derivative with respect to time, that gives you the velocity. Take the derivative with respect to time, that gives you the acceleration. We can define it as the dx dt, I plus dy dt j plus dz dt k, or as the x dot I plus y dot j plus z dot k, or just the magnitude of the velocity in the x times I plus the magnitude of the velocity times j plus the magnitude of the velocity in the z direction times k. Any of those methods. And in the same way, we can talk about our acceleration vector, second derivative of the position vector. So anytime we need acceleration, we can take, if we know what the velocity is as a vector quantity, we can just take the derivative with respect to time and we have the acceleration. Or we can take the position vector of the original point, differentiate, that gives us velocity, differentiate, that gives us acceleration. And these are the different ways we can write those. You got that? Okay. Not so bad. Let's move forward and see how this works. All right. So here we have, once again, we're looking at planar motion again. We have some particle at point A. We're defining it as the position vector r, right? We figure out, measure what the x is and multiply it by I, and the y multiplied by j. You can see that, how that's defining the position of this point. Since we only have planar motion, we can forget about the z because everything we're going to assume is in the zero position z. We can now take that position vector, take the derivative. That's going to give us the velocity vector, and that will be tangent to the path. We then can take the derivative of that velocity vector and that will give us the acceleration, and it will tell us precisely the direction, whether it happens to be parallel, whether it happens to be perpendicular, or whether it happens to be somewhere else. The vector acceleration tells us everything we need. If we actually want to know what that change is, you can see here we've got the velocity in the x and the velocity at the y, and the resultant velocity shown at point A in the left-hand graphic. We can actually talk about this in more understandable terms as the x velocity and the y velocity. We can find out what the direction of the path is at that point by just calculating the angle between these from like a convenient horizontal. So if we just take the tangent of theta is just Vy over Vx, solve that for the theta, that tells us what that angle is. The magnitude of the velocity is just Vx squared plus Vy squared, square root of all that. And the magnitude of the acceleration is calculated the same way. This is old information applied in a way that we're not used to applying it so rigorously, and that's what scares us or makes it feel hard. But it's actually quite simple and rooted deeply in what we should have already learned from physics. Got that? All right. So let's go and start looking at some real world kind of examples. The trajectory of a projectile can be defined with these. We already looked at this a little bit with our rectilinear motion idea. But let's say we throw a ball or shoot a projectile. We shoot it with some kind of horizontal and vertical velocity. It's going to tend to have a trajectory which is climbing, but remember it's resisted by gravity. Gravity's trying to pull this thing down to the center of the earth. So it's going to be going up since we had an upward velocity. Eventually it's going to come down since we have acceleration going toward the center of the earth. Meanwhile, it's moving in the x direction the whole time. We're going to make some gross simplifying assumptions to keep this simple, and later, after we get more education and practice, we can start adding in things that we've ignored to get better and better, more accurate solutions at the cost of simplicity. Okay, so if we talk about this, generally when we talk about a projectile, usually what we want to do is start off by showing what is our coordinate frame, or where are we going to put our coordinate axes. Typically, we're going to want to identify the coordinate axis origin at the starting point of our motion. We could actually put it anywhere, but usually that will simplify things a good deal. So if we put our origin at the start of our path, we can define x to the right and y up. And now we can say, okay, we shot off this particle with some initial velocity at some angle from the horizontal. So our theta and our v initial are our two input starting points. Okay, you want to keep in mind for this, we're going to talk about this in a moment. We're going to ignore a number of things, including like drag and such. You know, the idea that when you throw something through air, their air resists the motion. That's going to slow it down. That's too hard. We'll talk about that in later classes. We're going to often just ignore that and say, that part's negligible. So there's nothing inhibiting the x motion. Now notice though, when we throw it up, most of the times we do this, we're going to be on some planet like Earth. Earth has gravity, which is pulling everything to the center, which means anything we throw is getting accelerated toward the center of the Earth. If we throw it down, it's going to be speeding up. If we throw it up, it's going to be slowing down and then speeding up as it drops. So this is going to affect our vertical motion. So you'll notice our initial velocity means we've given it a positive x and y velocity. We can calculate what the components of velocity are, and we need to be very proficient in doing this. We'll just take that initial velocity VO, multiply it by the cosine of theta, and that's going to give us our x velocity. If we take that VO sine theta, that's going to give us our y component of velocity. If we want to talk about the instantaneous velocity at that point, it's just going to be that VO cosine theta I plus VO sine theta j. That completely defines the velocity at that point. The position initially was at 0, the R position, and we have the velocity at that point. And now we can go and evaluate the motion. Now, the thing that makes this hard is it's not like we can just plug into equations and just operate on the equations. We're often going to have to go look at, okay, we have an equation relating position to time. We have an equation relating velocity to time. We have an equation relating position to distance and velocity to distance. And we're going to take these equations, you can think of it as a toolkit, and we're going to open that up and spread out the tools that might apply until we figure out the appropriate tool, sometimes putting these tools together to define our motion. Another thing that makes this hard is you have to understand some basic ideas and be able to apply those to these equations or these tools over and over and over again. For example, what do we know? We know at the initial position, we're calling that 0, is that initial position. We know that initial velocity. We know this has a downward acceleration over the entire time it's moving until it stops. We know that we're not doing anything to affect the speed in the x direction. We're saying there's no drag, so we're ignoring that influence on both our vertical and horizontal direction. Now we need to make another leap of judgment. You have to recognize, and most of you would think, oh yeah, that makes sense. When you throw anything upwards, when it gets to the top of its trajectory and starts coming down at that moment. So to go up, we have to have an upward velocity, right? But in order to go down, we have to have a downward velocity. At the top, the velocity is 0 at that moment. So with these problems, we're going to deal with, we've got initial position of 0, we have a final position of 0, and we don't know where the top of that arc is, but we know that the velocity, the vertical part of the velocity, has got to be 0 at that point. And we're going to use that to determine certain things. So position 0, velocity 0 at the top of the trajectory. The velocity, we knew what the initial velocity was. We don't know what the final velocity is. It's going to be affected by all these factors. We don't yet know what the position is up at the top of the trajectory. We do know the position at the end is 0, just like the position at the start is 0 for this particular problem. We know gravity is constantly pulling us downward this whole way. So what we're going to do is use the equations and orchestrate them, these tools, such that we can solve the problem using what we know and the equations that we believe apply. Okay? At any particular point, we could calculate what the position is using those equations. We could calculate what the velocity is using those equations. We could calculate what the acceleration is using those equations. Okay? So our initial position is 0. Our velocity in the x is also 0. Our acceleration in the y is g, but it's acting downward, so it's negative g, 32.2 feet per second squared, 9.81 meters per second squared if we're on this Earth, right? And it's always going to be negative because it's always pulling toward the center of the Earth. So it's acting since we defined y as up, this is a negative g pulling us downward. These are just the magnitudes of those values. So v, x is just the x component of the initial velocity, which is VO cosine theta. Vy is the initial velocity. So this gives us the equation for what the magnitude of the velocity is. And for y, what we have is the initial velocity, Vy, which was just VO sine theta, we'll see in a second, minus gt, because the acceleration is resisting it, since the acceleration is plus acceleration times time. Remember, VO plus AT. The VO is just in the y direction, is just VYO, which is V sine theta. And the AT is, we're talking AY, which is negative GT. And so that's why we just applied that equation. We get it like this, which you can write like this, okay? And now we can talk about the position x is just v times t, right? Since velocity is position over time, the position is just velocity times time. However long we're going at that constant velocity, that's going to tell us how far we've gone. So VO cosine theta is our initial x velocity times t. That is our equation for the position. We can use this to define the position at any point by just plugging in VO, the cosine theta, whatever angle we put that at, and the time that's elapsed. Also, our y is now just YO plus VO, the y position, the y velocity t minus, remember this is just the position, S equals SO plus VT plus AT squared, and the A is negative. And since we're talking about the vertical component of that, we're just plugging into that S equals SO plus VOT plus AT squared, right? 1/2 AT squared. We're just plugging in, since we're talking about vertical, we're plugging in the vertical components. So instead of S, we're saying Y. Instead of SO, we're saying Y0. We have the velocity in the Y direction initially times the time, and we have the component of acceleration that's affecting this, which is just G. Okay, that was our equation we saw last time. We can apply this, plugging in our values. Now we can go back and say, wait a minute, V dV equals A ds. This is just done by, remember we defined this last time where we just took the definition of A as dV dt, the definition of V as ds dt, and then just put those together. And we got this relation, V dV equals ADS, not necessarily one that's intuitive, but one that we derived and now can use. When you integrate this, this means we can integrate both of these. We end up with a 1/2 V squared plus AS, which we can now write across the limits, right? V2 squared minus VO squared, which we're just calling V squared minus VO squared, equals 2A delta S, which is just Y minus YO. We can use that to come up with this relation. The velocity at any point squared is equal to the initial velocity squared, and this is talking about the Y component of that, minus 2, the acceleration of gravity times Y minus YO, whatever that position is, minus YO. So we can use these different equations to relate and solve these problems. We're going to see this in some examples in a minute. Notice these are the same equations we were using before in our rectilinear motion. We're now just applying this to curvilinear motion in an even more general sense. We're neglecting aerodynamic drag, the curvature of the Earth, the rotation of the Earth, the effect of altitude change on G. This makes it way simpler. This means this isn't going to be completely correct, but it'll be close enough for government work. And later, when we get more knowledge and experience, we can try including some of these components, which will make these harder or even unsolvable in some cases. Okay, let's look at an example. Here's a little projectile motion, almost identical to our case where we laid out the equations. Now you notice there's one little trick that makes it slightly harder, is we're not looking at the initial and final positions are not the same elevation. No big deal. This is not hard as long as you keep from becoming afraid to move forward. We have a projectile, it's valid. So what we have to do is, with our given find solution, it's useful to write given and write out what we know. We can see we have a coordinate system. We can either define our coordinate system from the lower surface, x to the right, vertical up, or from the point of where we start the motion, x to the right and y up. That's the one we're going to use. It's, in this case, slightly easier perhaps. Because of the definition of our coordinate system, that will define whether we start off at 0 or at 150 meters or at 0 meters, and it will affect where our final position is, either at 0 meters or a minus 150, okay? But we have this initial velocity, 180 meters per second, and we know the angle. So we have the theta, we have the VO, we have the initial position. We can actually do everything. But once again, we're going to have to use the initial position, the initial velocity and its components, the final position. We're going to have to use the idea that we have gravity resisting our vertical motion the whole way, and the idea that the top of the path of the trajectory, our vertical velocity is going to be 0. We're going to pull all these together to solve this problem. Okay? So this is just This is Beer and Johnson's problem, and this lays out the different things we're going to do. We're going to consider both components separately. We're going to apply our equations of motion in each direction, and then we're going to evaluate this at different time steps or different positions in order to solve the whole problem. Stay tuned. All right, so once again, it is quite helpful to sketch this. We can see our initial velocity is 180 meters per second. Our initial position, we can either use 150 if our coordinate system is down here, or 0 if our coordinate system starts here. We know our acceleration, written more explicitly, is negative 9.81 meters per second squared. That's our vertical acceleration. And the acceleration in the x we're going to assume is 0. We know that we're uniformly accelerated. We use that term to say that g is not changing. The acceleration is not changing. We're always accelerating towards the bottom of to the center of the earth. It's never changing. We call that a constant acceleration problem, which a lot of our equations are derived that way. In this particular case, we're going to define our coordinate system with x to the right and y up from the origin, which is our starting firing position. We could have done it the other way. We're going to do it this way. That means our final position is at minus 150, and our starting position is at 0. Notice we've shown the initial x velocity, which is VO cosine theta, the initial vertical velocity, which is VO sine theta. We have that angle of that velocity shown. We have a little vector showing that we've got acceleration in the negative direction, negative vertical direction. We've sketched this out, and we've identified what we need. These are the equations that we have. We can calculate our vertical component of velocity, our horizontal component of velocity. We can also look at the equations that apply. V equals VO plus AT is our general equation. We plug in our values and we get this equation 1. Y, remember we call that S equals equals VOT plus 1/2 AT squared. That's our general equation, which we now are applying to the Y direction in equation 2. And that equation that we kind of re-derived quickly a moment ago, that velocity at any point squared is equal to the initial velocity squared plus 2AY. Remember, our A is negative, which throws that negative sign in equation 3. And for horizontally uniformly accelerated, where the uniformity of the acceleration is 0, we can show positive x to the right, and we can write those out that way. You got that? So with these building blocks, we're now ready to start solving this problem using some other things we can observe. So here is our little sketch. We know the horizontal distance. We can calculate that. Projectile strikes the ground where the vertical position is negative 150. We need to recognize that. We can substitute that into that second equation, which we're repeating right here. And when we do that, we get this equation relating time. Now, you look at this, oh, look, this is all information we know except for time. Unfortunately, we got two values in there, one of them squared, so we got to use the quadratic equation to solve it. When we use the quadratic equation, often we're going to get a root that's meaningful and a root that's not. Sometimes we'll get two solutions that work, and we'll have to define which one is correct or more correct or happens first. In this particular case, the negative root means nothing. We take the positive, and we can't go back in time. We take the positive root, and we find out that the time of when we strike at the bottom, just from our this first equation that we're using, is 19.91 seconds. Now we can use that to learn a lot of things, or actually to plug into our equations and do more. So remember, we plug this into our x equation, x position equation. We can find out where this thing hits. This thing hits at 155.9 times t. The longer you have, the further it goes. That is our general equation for that. So if we plug in the time which it hits, which we got from the vertical information, we find out where it actually hits, at what position, what x position this projectile hits the ground. Now we know that the max elevation occurs. Remember, I said we're going to have to pull these things that we know out and use them over and over again. We know the vertical velocity is going to be 0 at the top of the trajectory. So we can use that in our equation, in our third equation there, to calculate what position is the top of the trajectory. And then we can figure out what the elevation is. We can figure out what the elevation is from that. Remember, this is y is relative to the initial starting position. So coming from the bottom where it hits, that's 563 meters above the final place, 413 above the initial place. So that's how we solve that. Here's another similar problem. Here we have a pitching machine. We know the initial velocity, which is VO. It looks like it's horizontal initially. Once again, since we're on Earth, most of these problems are going to be on Earth, so we've got a gravity, which is accelerating this thing downward. We can see that the height at the final position to be 42. That's going to be our final vertical position. We can see the initial vertical position here. Now, another thing you got to be careful of is, remember, when we're using the U.S. system of units, we need to be feet and inches, right, and pounds. When we're dealing with SI units, we've got meters and seconds and newtons. So in this particular case, while a lot of times we're going to get information in inches, we're going to have to convert that into feet when we're using our acceleration and those kind of things. So you got to be really careful with the units for any problem, but especially with the U.S. system of units. And it looks like we want to find the height. Oh, we know what the height is. We want the initial velocity. What velocity this should be shot at if we want to have a 42-inch height at the baseball player's swinging position 40 feet to the right of the machine. Once again, this is just going to be applications of our principle where we're looking at the x equations and the y equations. We're going to assume those are independent and solve this puppy using the pieces of information that we have and the things that we can know from the way we know things work. Okay? So here's that little problem. A little sketch helps. We can see that the final position is at x equals 40. The initial height is y equals 5. The final position is y equals 42 inches, which we can't use. We have to first convert that to feet. Instead of 42 inches, we need to divide that by 12 inches per foot to get the feet position and use that in our equations. So we're going to analyze our y motion. We use this equation. Our position equals the initial position plus the velocity times time minus 1/2 gt squared. Remember, the vertical velocity was initially 0. The initial position is 5 feet. And we have 1/2 g, 32.2 feet per second squared, and time, which we don't know. We can solve this for time. Once we have that, we can solve our x coordinate, which the position is just the initial position, which we're assuming is the origin, the initial velocity in the x direction, which is just that initial, since it was shot horizontally, that's the full initial velocity. We don't know what that is. Times time. You can now solve this for the initial velocity based on that time calculation we already did, and we find out what the velocity is. So you'll notice here, we've got a bunch of equations that apply in certain cases, like constant accelerated motion, and we're using what we know about the universe, like the idea of gravity, the fact that the velocity, the vertical component of velocity has to be 0 at the top of the trajectory, and what our positions are that we know about in order to unravel the solution for this problem. Okay, let's practice some other kinds of problems. Let's just think about this. We have 2 model rockets, and they're fired at the same exact time from some kind of ledge, which is h above the lower position. We're going to neglect air resistance, which we're going to do in all of this class, and we want to know which rocket will hit the ground first. So is it A, the one that goes higher? Is it B, the one that goes lower? Do they hit at the same exact time, or does the answer depend on H? So think about that for a few minutes. Maybe stop the video, do some scratching and calculating, and think about it. And once you think you've got your answer, then come back and let's continue. It's actually B, and if you want to know why, here's why. Remember, our vertical position is y plus VOT minus 1/2 GT squared. If we look at these two trajectories, we see they're both accelerated the same downward, same amount. Since the first rocket, A, travels higher, that means it had to have a larger vertical component of initial velocity in order to go to that height. Since they have the exact same downward acceleration, then that one will have to take longer to get down. It has further to go up and further to come down. They're both being resisted the same way. Therefore, this has to be B. You want another one? All right, let's think about this. Ball A these are out of Beer and Johnson, by the way, these ideas. Ball A is thrown straight up. Which of the following statements about the ball are true at the highest point in the path? Are the velocity and acceleration both zero? The velocity is zero, but the acceleration is non-zero? The velocity is non-zero, but the acceleration is zero, and neither one is zero. So think about that. Stop the video. Think about it. Scratch on your paper. When you're done, come back. All right? Remember, our velocity at the top of the trajectory, we're moving up. We have to have an upward velocity or we're not moving up. At some point it stops and then it comes back down. Before it's going up and then it's coming down. In between, it's dead stop, zero. But the acceleration is not zero because it's always accelerating toward the center of the Earth. Acceleration is constant, non-zero. Here's another little question. Is it possible for the vector, this is out of Costanza, Gray, and Pleshett. Pleshett? Pleshett's not the right word. I forget his name. Anyways, it's defined on the start there of my video. Is it possible for the vector v shown to represent the velocity at point P? So stop the video. Think about this. When you're done, come back. Answer? No, can't be. Why? Remember, velocity has to be tangent to the path. That vector is not tangent to the path, can't be correct. Okay, you got that? Is it possible for the acceleration to be off in the direction shown? Also no, because if the acceleration were that way, this thing never would have turned down. It never would have turned the velocity down. To turn the velocity down, bring it down like this, the acceleration is going to have to be aimed down somewhere, have some component in that direction. Oh, it looks like I spilled the beans. That was this problem. You got that? Okay. Here's another little one. We have a ball thrown, so the motion is defined by the equations now. So now we're given the equations. That sometimes happens in some of these problems. X equals 5t, y equals this. Where are x and y are expressed in meters, t in seconds, determine the velocity at 1 second. Okay? You can see you have the position vector as a x and as a y. We want the horizontal distance. Since we're already given the equations of motion, we can just differentiate these puppies. Differentiate the first equation to get the horizontal velocity. Differentiate the second equation to get the vertical velocity. Then we can just put those together for the root mean squared value. Calculate the angle, and we now know what the velocity is and the angle. Now when we show our answer, we want to show magnitude with units, proper sig figs. Beer and Johnson, Merriam and Craig, nearly every statics, nearly every dynamics, nearly every structural mechanics book uses the same simple shorthand rule for significant figures. 3 significant figures for everything except for something that starts with a 1, where we use 4 significant figures in our answer, and we box the answer. We need to show magnitude and direction and units. The best way to show the direction is to put a little horizontal with a little angle thing and a vector showing that it's just down from that. That's what the negative 37 means. Since this would be positive, this is negative 37 is right down here. So you show the X with a little angle symbol, and that's the way we'd show our answer, except we would box that answer. Now we can get our horizontal distance, and by just plugging into that and solving for that. You got that? Here's another little example. We have an airplane. It is used to drop water on brush fires. It's flying horizontally in a straight line at this velocity. Now you got to look at this velocity. Wait a minute. I'm going to have to convert this. This is miles per hour. And what do we need? Feet per second. So we're going to have to convert miles to feet and hours to seconds. We have an altitude of 300 feet. Determine the distance at which the pilot should release the water. So if we want to release the water, we have initial position here. What we're going to be trying to do is calculate this X position, and it's going to be a function of how long this takes to drop, right? We're going to have to use the vertical information and the horizontal information. So once again, we're going to grab this is our converted velocity, right? We're going to place the coordinates at point A. Notice we've got the vertical position here. X and Y are shown like this, and our horizontal position. We can use our equations to solve for the information we need, first for the time, and then for the horizontal position. Got that? You may want to stop the video, work that on your own, make sure you understand the what and the why. Last example. This is out of Gray and Costanzo's book. And Plantema, that's the word. I don't remember. So here we have, this is not a Ferris wheel. What we have is an aircraft flying in a circle, and the rest of this is just showing the path. We know the velocity is going to be tangent to the circle, and we can see we're defining theta from the downward from the center of the trajectory. Our actual origin is down there at point O, and we're using I, J, K kind of components. We have this airplane is performing a loop of constant radius. When theta is 120, which is way over the other side, the speed of the airplane is 210 miles per hour, which we have to convert to feet per second. Modeling the airplane as a point, which basically means particle. Find the velocity of the airplane at this instant using the component system shown and express your answers in feet per second. So to do this, this is the solution to that. We can see the velocity of the aircraft is tangent to the path. The path is centered at C. We can see the tangent is perpendicular to the radial line. We can see our velocity at any point is just going to be that initial velocity, that velocity times cosine theta I plus sine theta j. All right, that's pretty simple. Our velocity is just the magnitude of that. Therefore, at 120, we can just calculate what that is. That is the velocity. Remember, that's the velocity when we're at 120, where our position is, our theta is 120. At different points, we're going to have the same velocity if we're flying at the same speed, or we may have different ones. But actually, even if we're at the same speed, we're going to have, you'll notice, this is negative x component and positive y component, but that's going to change as we change at different angles. Different angles will have different values. All right. You may need to rewatch this video. You're probably going to want to spend some time practicing with these problems that I've laid out. If you want more practice, grab your copy of Beer and Johnson or Merriam and Craig. There will be example problems worked out. There will also be problems in the working problems part, many of which have answers in the back of the book you can check yourself. Enjoy.